Good morning, and thank you for joining us for this APC Media webinar with the focus of safety, reliability, and ROI, protecting your operations and budget. I'm your host today, Rachel Linke, the Director of Communications for APC Media. And today our presenter is Josh Robinson from the company Iris. Our CEO and Technical Director at APC Media and President of EPRA, Alan Ross, was actually going to be moderating this today, but unfortunately he was unable to make it. But he wanted me to introduce Josh by saying the following. Josh Robinson is the Vice President of Business Development at Iris North America, but he is much more than that. The personal decision that Josh had to make about whether to continue in medical school or take on this new role must have been a hard one, but we are certainly glad that he has chosen to take on the challenge of making safety and reliability a priority in industrial North America. His passion for the practitioner, for their personal safety, and for the reliability of facilities throughout the country will change the way we think about electrical systems in the future. At APC Media and the Electric Power Reliability Alliance, we are glad that he has chosen this path. So thank you so much for presenting for us this morning, Josh.
Morning, Rachel. Thanks for that fantastic introduction. I'll go ahead and kick off and try and live up to that.
Absolutely.
So,
I know you will.
Just to come back around to it, morning everyone, my name is Josh Robinson and I am the Vice President of North American Business Development at Iris. And I'm here today to talk about how safety and reliability programs can help deliver ROI to your organization. Today's agenda is going to be a brief introduction to Iris, then we'll go over understanding how assets fail, an overview on designing for safety and reliability strategies, then we'll move on to managing risk. We'll touch upon the upcoming skilled labor shortages, the total cost of ownership impacts from a design for safety and reliability program. We'll go over carbon footprint impacts, then we'll touch upon a case study, and we'll finish with a summary and any final questions anyone may have. So just a little about your presenter today. My name is Josh Robinson and I am a certified reliability leader. I have a degree in business, originally from the University of South Florida, though going down that medical school route, I picked up a ton more prereqs than that. I have a Cat 2 infrared inspector certification and a Cat 1 ultrasound inspector certification. So been in the field doing inspections for parts of my career. I live in Bradenton, Florida, and my hobbies would be my 4 girls, kept trying for that boy. Then I bought 3 cats, which I thought was, some of them were boys, turned out they were all girls. So I had to go back again and buy 3 more dogs that are all boys, which leads me to my true hobby of boating to get away from it all. So, about Iris. We're the world's largest manufacturer and designer of electrical safety, maintenance safety devices, basically tools that allow you to be in a closed and guarded condition away from danger whilst doing your job. We're based in Bradenton, Florida. We have sales and technical support available in over 60 countries. We're an online and site-based infrared, ultrasound, and partial discharge training provider. And as of 2022, we launched Safe Connect line of thermochromic indicators, which I'll touch upon later. These are the Iris maintenance inspection windows. They allow closed panel inspections in the visual, infrared, and ultraviolet spectrums. We have the ability to add ultrasound detectors on the inside that can be used with a variety of different pieces of equipment. They're available in round, rectangular, and if what we have standard doesn't work for you, we'll make a custom that does. Then we come over to our IoT solutions packages. We have our Delta T temperature and humidity monitoring sensors. They allow you to get constant data from your equipment whilst no one is out there taking the data down. We have an eSentry Connect NFC data management and labeling solution that allows you to put that data up into the cloud so that everyone can access it from wherever they are in the world. And then our Sonus Connect online partial discharge and ultrasound equipment solutions allow you to do remote online partial discharge and ultrasound inspections of your assets when no one's there. And our newest product range is the Safe Connect thermochromic solutions. Now, what these Safe Connect thermochromic solutions do essentially is they add memory to infrared scanning. If you're looking inside a panel and you're looking with an infrared camera, great, you're doing proactive inspections of your equipment, but the problem is you only see what you're seeing when you're seeing it. Say the panel you're looking at only runs once a month, and then it's overloaded and you don't know about it because you're not looking at it at the time when the panel's running. Well, that's why we brought this out. If you only have a 12-month inspection cycle, you're not going to know if things happen in between those 12 months. But if you leave one of these clips on your system and it changes from purple to pink, it tells you that the system had an issue when no one was looking. It's an over temperature indication solution, and it essentially adds memory to your infrared scanning. Now, to touch upon Walter Deming, this is one of my favorite quotes. It's, your system is perfectly designed to give you the results you're getting. What does that mean? If you like the results that your system's giving you, the data is great, change nothing, you built it right. However, if you don't like the results you're getting, then there's a problem with your system, and maybe you need to redesign it to give you better results. Now, when we talk about maintaining equipment, language is everything. And we need to shift the mentality from maintenance as an overhead to reliability as a necessity. If you ask someone if they want more maintenance, the answer will often be no, because it's seen as a cost. Who wants to spend more money? Maintenance isn't really doing anything. Let's just cut that budget. Now let's shift that perspective to reliability. In order to get equipment reliable, it needs to be maintained correctly. Reliability is always going to be seen as a necessity and an asset. If you ask the same question and say, hey, do you want this equipment to be more reliable? Nobody's ever going to say no, because reliability is a necessity, maintenance is an overhead. Language is everything, and we need to send that point home. So I'm going to touch upon the reliability process. And this slide goes over the design stages of building a program. And people think that you build the system, and when you get to the maintenance part, you just maintain the system that you built. But the problem is that reliability in a nutshell is all about defect elimination. So when we're designing the system, we can introduce defects. We need to design them out. When we're buying our parts, again, we can introduce defects. We need to buy the correct parts. When it comes to storing the parts you got, you better be storing them correctly. You better be turning them over and making sure they work, because otherwise, when it comes to putting those parts in, again, you're going to introduce defects. Install and startup. We have to use precision maintenance. Be very careful here as to not introduce defaults and make the equipment likely to experience infant mortality. When we operate our system, we can again carelessly introduce defects if we don't operate it with care. And then with maintenance, yeah, we can introduce defects, can also take them out. But the one thing we cannot do, we can't maintain our way to reliability. So what does that mean? We have to put weight into each of these steps, being careful to make sure no defects are being added. And in fact, we're removing defects as we go along. Just remember, reliability is all about defect elimination, and you cannot maintain your way to reliability. This is a histogram from Wilson-Ledet, and it shows how random failure pattern is common. 84% of failures are caused by poor operating and maintenance work practices, which result in random failures. And what this histogram shows us is 300 of the same component, and this is each of their failure rates. Same component, different failure rates. Now, if we rearrange that histogram, put it from fastest failure rate to longest failure rate, what do we see? Roughly half of our assets are failing in the 5-day period, and roughly the other assets are failing in a 10-day period. So how do we maintain these assets? If we use a time-based strategy of 5 days because half of our assets are failing in 5 days, then what we actually did is dramatically over-maintained half of our assets. And if we maintain our assets on a 10-day cycle, then we're dramatically under-maintaining our assets that fail in the 5-day cycle. So this asks the question, what do we do? Time-based clearly doesn't work because things don't fail on a time-based cycle. So what we have to do is move from time-based to condition-based way of thinking, where we see what the assets are telling us and then move forward from there. Now, these 4 studies below are major studies on reliability-centered maintenance. 2 were done by airlines, the United Airlines study and the Bromberg study, and 2 were done by the US Navy, one on its surface warships and one on its submarines. The studies went over the different failure patterns and the distributions of those failure patterns. And there's some interesting results from those studies. Now, the first 3 failure patterns we see are the bathtub curve, the wear out curve, and the fatigue curve. This shows us that bathtubs, typically 3 to 4% of the time, are the way that assets fail. Wear out 1 to 17% of the time. Fatigue 3 to 17% of the time. And this is the data from each of the individual studies that shows it's pretty consistent. Now we come to the next 3 failure curves, and this is where we see the majority of failures. The initial break-in period is 6 to 11%, random is 14 to 22%, and infant mortality makes up the majority at 29 to 68%. Now, what is infant mortality? It's when you put your equipment into running conditions and you don't do a great job at either being careful in what you're doing to not introduce any defects, or the alternative is you go back into your equipment, you touch things, tighten them, physically interact with the gear, which resets the infant mortality curve. Now, from these studies, we see that the Navy doesn't quite agree with the general business results. And the reason for that is that the Navy practices super precision maintenance. The book on doing any activity in the Navy is 5 inches thick, and it tells you everything. If you've got to turn a bolt, it's telling you how to turn that bolt, how many degrees, which temperature to do it in, how you put lubricant on it afterwards, and then where you'd put it into a bed and tuck it in at night. The maintenance practices are fantastic, but they typically aren't realistic in the world outside of the military. Then we come to random failure patterns, and you see more random in the Navy because they've worked out the infant mortality problem and come up with a better way. So what are the effects of time-based maintenance on infant mortality? This shows us different times where you would be inspecting equipment on a time-based maintenance schedule. But the only point you should actually be doing anything with your equipment is right here. You know why? Because there's been a change. Your equipment's telling you, hey, something's not quite what it once was. Let's go in there, take a look, and conduct repairs based off the results of taking a look. Touching the equipment here, 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 and here on a time-based schedule did nothing. There was no reason to interact with equipment. Here it's trending in a better way. Here there's no change, no change, no change. Oh, change. Let's go take a look. We can inject defects every time we physically interact with equipment. So what does that mean? Don't interact with equipment. There is no reason to touch equipment for no reason. All we do is introduce the opportunity to inject defects, and we reset the infant mortality clock, which, as the slides prior showed us, was the time where we're most likely to experience failures. So what if we could redefine a maintenance strategy? Said earlier, as much as 68% of failures are infant mortality. We can improve this by avoiding unnecessary maintenance, how we design, buy, install, and store and start up equipment. Unfortunately, as much as 80–90% of failures occur in a constant yet random mode. For this, we must monitor the condition and only interact with it when we see an onset of failure or a reason to do so, because 77 and 91% of equipment has no end of life. So let me give you some examples of maintenance strategies. Strategy 1, there's a shutdown required. The asset isn't broke, but we're not fixing it. But we're fixing it anyway, sorry. That don't really make much sense. Strategy 2, no shutdown required. The asset's inspected, 0 faults were found. The results were logged, the asset was left in service. Sounds a little more logical. Strategy 1, isn't broken, we're fixing it anyway. Planned time-directed maintenance. That's what it is. Strategy 2, we're looking at what's going on. There are no faults. We record the data, we set our trends, we leave the asset in service, and we come back and look at another date. This is a condition-directed repair program. The conditions didn't direct a repair, so we didn't do one. This leads me to a really fun fact. I bring it up all the time in presentations, but the Mars Lunar Rover, it was designed by NASA engineers to last 90 days. Do you guys know how long it actually lasted? 14 years. This is a highly engineered piece of equipment that people didn't think would last longer than 90 days, but it lasted 14 years. Why? There's nobody on Mars to touch and mess with things, tweak, break, crank, try and fix it. Like we said earlier, if it's not broke, don't fix it. And this system lasted for 14 years on a 90-day design. You know what killed it in the end? The batteries died. Certain components will eventually wear out over time, but this machine went far above and beyond because people left it alone to do what it was designed to do. This brings us to about the first third of the presentation. I'm going to stop and see if anyone has any questions, anything they need clarification on.
So Josh, I have a question that I wanted to ask while we have a second here is, so the infant mortality rate for electrical equipment is quite different than that of mechanical equipment. Why is that, and what does that mean for the average practitioner?
That's a pretty great question. So infant mortality rate, regardless whether it's electrical or mechanical assets, it's all about touching equipment and injecting defects into the system through mistakes, or touching things that didn't need to be touched, which can lead to early failures due to the introduction of faults. I personally think that the biggest difference in infant mortality of electrical and mechanical assets is that electrical failures can be far more catastrophic for businesses, as when the power goes off, everything downstream from it is now affected too. This isn't always the case with mechanical assets. So to an average practitioner, this means they should probably be more careful when interacting with electrical assets, as the criticality of equipment tends to be greater than mechanical assets, in my opinion.
Oh, that's a great response. That's great. I think that's all we have for right now. So if you want to continue on, we'll check back in with more questions.
Perfect. Thanks so much. Okay, rolling on. This leads to the question, where do we start? Want to make things better? Where do we start? And it comes down to the same thinking that got us into these problems is not the thinking that's going to get us out. Same old thinking, same old results. Maybe we should look at things differently than we have in the past. Let's look at planned maintenance optimization programs. Why do you do the PMs you do? Someone tell you to do them? Is this an example of the monkey case where monkey see, monkey do, we always did it? Let's take a deeper dive into it. We really shouldn't assume that our PMs are correct. This is a study I'm about to present done by John Schultz of Allied Reliability. And it goes over 20,000 PM tasks within an organization. When they analyze these 20,000 PM tasks to see what the validity of them were, these were their results, and they're quite striking. Only 11% of those 20,000 tasks could be used as is. That means that 2,200 of these tasks out of 20,000 was the only things that was being done that had a valid reason to be done. 8% of the tasks were deleted altogether. 33% were replaced with a condition-based maintenance program. 26% were re-engineered by FMEA. 7% were transferred to operations, and 15% were transferred to lubrication. Look at what that data shows. 11% were valid as is, but we did it anyway, right? Maybe we just need to look at what we're doing and ask ourselves why we're doing it. Replacement strategies. So we're all about moving towards a condition-driven repair model. The replacement strategy is designed to replace outdated legacy time-based maintenance inspections, but still you want to manage the risk of failure. We just don't want to touch things. And at Iris, we're big on designing for safety and reliability. The reason is that safety and reliability are two sides of the same coin. In order for an organization to be reliable, it has to be safe. Because if an organization is unsafe and people are getting hurt, reliability is going to go down the toilet. By the same token, an organization has to be safe for it to be reliable, because the safer people are, the more reliable processes are, and everyone's doing better. Just remember the old saying, keep it simple, stupid. Inspection programs that use CAS and EMSDs ensure the task of data collection and equipment monitoring are simple, repeatable, and using the KISS principle, which states that systems perform best when they have simple designs rather than complex ones. KISS is not meant to imply stupidity. On the contrary, it is usually associated with intelligent systems that may be misconstrued as stupid because of the simplistic design. In the words of Albert Einstein, everything should be made as simple as possible, but not simpler. And this means that we should just simplify a task, design it so that success is achieved with the maximum simplicity. You know why? Because to err is human. I don't care who you are, what you do, how you do it, all humans make mistakes. And it's not a bad thing. It's just something to be aware of. We need to make it known that it's inevitable and universal that people will make mistakes. This isn't a bad thing, but it's a learning curve where we just need to maintain systems that can help us to remove these errors that people will inevitably make. And this comes over to a term that the Japanese have. It's a poka-yoke device, and it's a device that stops you from making a mistake. Iris solutions are poka-yoke devices, and the design for safety and reliability strategy is all about making it so that people can't get hurt by putting in checks and balances to stop that from ever happening. Errors shouldn't be considered inevitable. We just need to make it so they don't happen using DFSR strategies. DFSR creates safer work environments. It assures a consistency of quality and results, makes problems more visible, and it lowers the cost of design and the cost of manufacture. Here are some examples of poka-yoke or mistake-proofing devices. This is a thermoclip. One's purple, one's pink. You can look at it and see simply that on the pink one, something's wrong. There's been temperature indication. No one would have any issue using that. Here's a UK plug socket, another poka-yoke device. It goes in, it has a very specific configuration of pins that will only be the only pins that will fit into that hole to get the power out of it. This is an infrared window, keeps you in a closing guarded condition while still being able to get thermal data from your equipment. This is a infrared window with an ultrasound port. Same concept, but it allows you to get ultrasound data from your equipment while it's in a safe, closed and guarded condition. And this one's kind of silly, but it's exactly the same point. A McDonald's bun gauge, it's a poka-yoke device. You've got your guys in the kitchen making product. Then when it comes to inspecting the product, guess what? It's a go, no-go gauge. Simplicity is key because it keeps people safer and it improves everything. Here's a study from a large chemical plant that shows the correlation between corrective and reactive work orders per year and the total injuries per year. This shows that the more corrective and reactive work we do, the more people get hurt. Makes sense, right? Because corrective and reactive work only occurs when a problem happens. There's no strategy to get it done, and now everyone's super stressed out and they're running like headless chickens to fix the problem, and that's when people get hurt. This graph shows the same point, reactive maintenance levels and total recordable injury rate. The more reactive our maintenance is, the higher our injuries are. And this final slide shows the same point, but when we move to condition-based maintenance work orders every year, the planning is better. And as the planning is better, people are less stressed, there is less pressure on getting the job done, and as a result, we see a decrease in injuries as more CBM work orders are used. We have to design systems to make it easier to do the right thing than the wrong thing. That is it in a nutshell. Defect elimination and helping people to not get hurt. Human error is inevitable, and using EMSDs allows us to design our systems and processes around this inevitability. So that brings us probably about the halfway mark, and I'm going to stop again to see if anyone has any questions or clarifications needed.
So Josh, I have one question I wanted to put through to you. How do we get people, management and supervisors, to move from time-based maintenance to from time-based maintenance to condition-based maintenance? And how do we make a case for change?
Well, that's a great question again. This would come back to the slides I brought up earlier, where it showed the histogram. It had the random failure rates of 300 of the same component, and we use it if we learned if we were using a time-based maintenance procedure, that we would either seriously over or under maintain half of our assets, as you know, there was no consistency in the time pattern to the failures. So what does that mean? We should only interact with the equipment when the equipment's given us a reason to do so. That doesn't mean that there are no time-based activities we should be completing, but the time-based activities we should be completing are inspections, and then we should be interacting with equipment when it tells us to versus the calendar telling us to, because the calendar isn't a friend of your equipment and it doesn't know what's going on as well as you do if you're actively inspecting your assets. And that would be my answer.
Okay, yeah, that's the only question I have for this section. So we can continue on, and if anybody has any more questions, you can go ahead and put them through the questions portion of the control panel on the right-hand side of your screen. So we'll just kind of wait to see for the next round if we have any more questions. You can go ahead, Josh.
Thanks, Rachel. All right, pressing on, guys. So now we're going to come into managing risk. What is managing risk all about? We need to assemble a team. List all of our failure modes and the effects of those failure modes. Once we listed those failure modes, now it's time to rank the severity of those failure modes. Then we need to look at what could cause the failure modes, rank how likely those causes are to occur, list process controls we could implement to reduce that risk, rank the probability of detection of these risks, and then from that data, we can then calculate our risk priority number. From the risk priority number, we take action on the objects with the highest risk priority number, and once we have taken action on the highest risk priority number objects, we recalculate our risk priority number to see where we are now. So this is FMES or FMEA, failure modes and effects analysis. We need to detect the failure, assign a severity number from 1 to 10, assign a probability number of occurrence from 1 to 10, and assign a detection number of 1 to 10. Then when we have these three values, we put them in here and we calculate our total risk priority number. From those numbers we get, we then plot each of our assets on a heat map with severity on one side and likelihood on the other. And we place them to know how we should be interacting with this equipment. Something up here, super likely risk of failure, and the severity of the failure is real bad, so that's going to be high on our heat map. Risk priority number is calculated using a number of different methods, but you know, the simple method is to use the likelihood of failure multiplied by severity of failure. The number can be used to assess the requirement maintenance systems to ensure that the risk priority number is managed within acceptable parameters. The above graphic again shows a risk priority number heat map. The thing about risk priorities it's all about your risk appetite and tolerance, and according to the Institute of Risk Management, risk appetite can be defined as the amount and type of risk that an organization is willing to take in order to meet their strategic objectives. Organizations will have different risk appetites depending on their sector, culture, and objectives. A range of appetites exists for different risks, and these may change over time. While risk appetite will always mean different things to different people, a properly communicated appropriate risk appetite statement can actively help organizations achieve their goals and support sustainability. Risk appetite and performance, while it's all about the pursuit of risk. Risk tolerance is about what an organization can actually cope with. Organizations have to take some risks and avoid others too. To do so, they need to be clear about what successful performance looks like. This question may be easier to answer for a commercial organization than for a governmental department, but can usefully be asked by boards in all the sectors. This is something worth noting. The higher an organization's risk appetite, the lower their management costs. And inversely, if an organization has a very low risk appetite, there's a lot more risks, there's a lot more costs associated with that. And so from here, we go back and look at that risk, the heat map of risk that we just drew. And we see that the stuff down here, it's not super likely, and the severity is not that bad. We'll just leave it on an annual inspection. Here, all right, we're getting a little bit worse. Maybe we'll check it twice a year. All right, now we're starting to get a little bit more concerned about the consequences. So we'll look at this 4 times a year. This one, we're going to look at 12 times a year. And over here, this is going to bring my operation down. So I need to know what's going on with that constantly. So we're going to drop in an online monitoring solution. Now that we've looked at that, we can bring down our severity number. Our probability of occurrence and detection numbers are going to increase. And what does that do to our data as a whole? It drops the risk of everything by simply implementing a designed for safety and reliability program. Risk priority number is now going to be recalculated due to these changes, and that lowering in the risk priority number is why we see the graphic on the screen that showed everything decrease. This brings us to the upcoming skills gap, and it's kind of scary when we're looking at some of the data I'm about to show. Like I said, wanted skilled labor, and we need to bridge this skills gap. For the last 3 years, the hardest segment of the workforce for employers to staff with skilled talent hasn't been registered nurses or engineers or even web developers. It's been the skilled trades, the welders, electricians, machinists, etc., that are so prevalent in manufacturing and construction. But if these skilled trade workers are difficult to find now, as Manpower's survey indicates, just wait a few years. The skills gap is likely to become more acute as over 50% of skilled workers in the United States were 45 years and older, according to EMSI, the Executive Management Service Incorporated, and 18.6% were between the ages of 55 and 64. This graphic represents what I just said, and here we look at electrical and electronics repairers. 75% of them are over 45, and then of that, 35% of them are over 55. Electrical and electronics engineering technicians, of this, 70% of them are over 45, and of that, 40% of them are over 55. Now we come down to electricians, the guys who are actually twisting bolts and fixing things in the factory. This one's real concerning because 65% of these guys are over 45, and of that, 25% of them are over 55. What are we going to do? The oldest group in the US is electrical and electronics engineering technicians. You know, while 38% of those jobs are held by workers 55 years older. These numbers are really concerning, guys, and the list with electricians is by far the largest of the skilled trades, with jobs of more than 600,000 in the United States. So this means that when we see this upcoming skills gap, we're going to have 600,000 jobs that we can't fill anymore. What's going to happen there? How are we going to bridge that? That's where EMSDs come into it, because people that have technical skills like electricians, electrical and electronics engineering technicians, electrical and electronics repairers, these guys have skills and they need to be using those skills as often as possible. And what an EMSD does is it allows you to remove some of the busy work so that they can get right on doing the work that makes a difference. That's going to be the way we get around this skilled labor shortage, until we can change the mentality of people that the only way for success is not a 4-year degree, and people in the trades have just as much of a shot at success, even more with these upcoming gaps that are going to be in the future. We just need to look at this, guys, and really come up with a way to bridge it. Now, this slide is from Ramesh Gulati at Jacobs Engineering, and it's really, really interesting. It shows the impact of designing for reliability and safety on the total cost of ownership of assets over their lifetime. So this shows that 75% of the total cost of ownership of an asset comes from the operation and maintenance phase, which is the majority of the factory's or asset's life. And only 25% of those costs are incurred in the acquisition phase. If we look at this red dashed line, it shows what would happen to the total cost of ownership through the life of the asset if during the acquisition phase, every opportunity for improvement was taken. See, it's not cheap when it comes to acquiring it. That's what scares a lot of people. But if you put the money in at the start, you can see that this trend decreases over time. And when you get the part here where you're at 75% of the cost you will experience throughout that asset's life, it offers you the lowest expenses on that asset. Then we come over to this orange line, which is the exact opposite. The total cost of ownership of an asset with zero asset management. We can see here that it's definitely the cheapest way to get an asset in the service. But what's the cost of that cheapness? All right, we're looking on the left in the acquisition phase, looks great. Management's loving it, right? But then when we get over here and we see 75% of the money we will spend on that asset in its lifetime, it is by far the most expensive way to go about things. Then we look at this yellow line, which shows, hey, we didn't take every opportunity for improvement when we were planning, designing, procuring the parts, building, installing, commissioning the equipment, but we did have an asset management plan on what we would do once we hit the operations and maintenance phase. And just having that asset management plan took the total cost of ownership down by 40% if you didn't have one. That's big numbers, guys. And this green line right here, this is non-monetary, but it's the value that we get outside of money by implementing an asset management program. And that's increases in productivity, throughput, OEE, etc., etc. These are things that we get better by doing the right thing. And this leads me to a different point of reducing carbon footprint. Lots of organizations are starting to get a push from the top to decrease their carbon footprint. That sounds like a pretty big task, right? Maybe not, because every time we do time-based maintenance, we have to have parts shipped to the factory. But once we order them, they've got to be driven there. And there's the gas, the fumes, the pollution generated by driving and moving assets around. Then there is turning your power off, right? You're running generators to run your heavy equipment. That's, again, creating pollution and increasing your carbon footprint. The money we're spending buying these replacement parts that don't need to be replaced and then throwing away, filling landfills up with parts that still had useful life in them. Super unnecessary. But if we shift the mentality from time-based to condition-based and only do things when they are actually necessary, then we're not going to be using all these parts we didn't have to use. And as a result, you're going to see a dramatic decrease in your carbon footprint, your budget, and your business will run more efficiently because you didn't do things you didn't have to do. So this is a case study on an inspection with and without an EMSD safety tool to allow us to be more efficient. So a data center currently had 250 critical electrical systems that were inspected annually. The reason they were inspected annually? The intrusive nature of the condition-based monitoring inspection they were doing. Miles, why was the condition-based monitoring inspection intrusive? Well, that's because these guys were doing it fully energized. They were doing it in compliance with NFPA 70E and 70B, but the panels were energized, which makes it a much more difficult inspection. As a result, the inspection was completed by 2 site electricians. They were only there to pull panels and make sure things didn't go wrong. And then you have 1 contract CBM company that's there to do the actual inspection. This annual CBM inspection currently takes 250 hours. So let's break that down. 42 hours of that time was spent on the CBM engineer putting on a PPE suit. 84 hours were the 2 electricians putting on their PPE suits. That's 126 hours. 250 hours were cover removal. 25 hours were the actual condition-based maintenance inspection. 250 hours were the cover replacement. 250 hours was the CBM engineer just waiting for the electricians to do their work. And 50 hours was the 2 electricians waiting while the CBM engineer did his work. This came to a total of 825 hours for the electrical inspection, and the whole job was 951 man hours. Of that, only 25 of those hours were productive, which is 2.6% of the labor that was done. Crazy. What does that mean? 926 hours, or 97.4%, were dangerous, high risk, unproductive labor. It begs the question, why would we want to do it that way if there was a better way? And there is a better way, and I'll show you that right now. This is the same analysis of that energized inspection, but now we're going to use EMSDs. We can now see that the CBM engineer has no hours in putting on any protective suits. The electricians have no hours in putting any suits on. You know why? You don't need to wear a suit anymore. There's no cover removal. The CBM inspection went up to 30 hours. Slightly longer, but only 1 guy doing it. The cover replacement, there is none because they never come off. No one's ever waiting because you can walk up to an asset and take your data, and there are no electricians waiting around. What did that do? It changed the job to 30 hours and 100% safe, productive labor. Let's do the math on that. The inspection went from taking 951 hours using a 3-person team to 30 hours using a 1-person team. Look at the picture. Looks easier, right? Definitely looks safer in my opinion. A real world saving on this one case was 97.4% of the man hours needed to complete this task. This leads me to the effect of condition-directed reliability programs. What do? It increases safety through hazard removal, increases availability to anticipate and plan for repair because you know what's going on with your equipment. It increases your time in service, decreases the need to get in and touch your equipment for no reason, reduces the maintenance in terms of man hours, as we just showed, and it reduces the collateral damage or the potential through degradation of mediation. What does that mean? In general, a complete reduced total cost of ownership. It's a no-brainer, guys, it really is. That leads me to, and back to Deming, as a lot of reliability roads tend to take us. Without data, you are just another person with an opinion. So let's move from time-based maintenance to condition-based maintenance, get some real data on our equipment, and not just be another person with an opinion. Let's really know what's going on and let's do better, guys. And now I'm gonna come back on camera so you can all see my face again, and I'll end on that with, are there any questions? And my contact info is below if anyone wants to get in touch with me after.
Sounds good. So I know I have one more question so far, and then we can wrap up, or we can, if anyone else has any additional questions, you can send those through. But I know there's been a lot of great information, Josh. If you could boil everything that you talked about down to one action that a practitioner or manager could take to increase their reliability and decrease the potential for accidents or injury, what would that one takeaway be? And maybe what is the second takeaway?
Okay, that's a good question. Yeah, how do we boil this down? We're going to boil down this whole conversation. It'll come back to the statement I said earlier. Reliability in a nutshell is all about defect elimination. And the place where you're going to eliminate the most defects is in the design phase. So it's all about making, tap the bloody webcam. It's all about designing your equipment properly to make sure that there are no defects in it, or as little defects as you can put into the system. Remember, you can't maintain your way to reliability, and as a result, design it properly. Then if I was to talk about the second takeaway, I would say we really need to shift from time-based maintenance to condition-based maintenance. Yeah, it showed in the data ahead that we can't accurately guess the times we'd need to do the maintenance. So by moving from time-based to condition-based, we could do, to bring it back to Deming, we could get some real data on our equipment and some real opinions and know what's going on in our facilities. But I would say that the biggest takeaway, reliability is defect elimination. Make sure that you design it properly with as many defects out. It will give you the lowest total cost of ownership throughout the lifetime of the asset. Second takeaway, move away from time-based because it's archaic. It's no longer how we should be doing things. Go to condition-based, only touch things and they tell you to be touched. Get real data and know what's going on in your facilities.
That was great, Josh. Thank you so much. I don't have any more questions. So to me, that means you did a great job explaining everything and we just don't have any more questions. So that's fabulous. So thank you all so much for coming. Josh, thank you so much for presenting all this great information. If anybody wants to contact Josh, his information is here on this screen. And this will also get sent to everybody who signed up and participated in the webinar today. But thank you so much for joining us, and you all have a wonderful day.
Thanks, guys. Have a great day. Signing off.